How about that for sound? Does that change anything? Can you hear sound now? I'm trying to use my good, I have two different microphones. Okay, no sound still. Okay, hang on. I'll fix. How about now? Now can you hear me? Yes. Great. Wait, I might have just added too much sound. Am I echoing now? I think there's a little bit of a delay in the stream too, so apologize for that. The trade-off between the latency and the quality. Since I'm going to be doing some like live coding during this one, I wanted the quality to be a little bit better, so I think echoey. Okay. I can fix that. Okay, you'll have to tell me if the echo is still here. Anyway, so there's a trade-off between latency and quality, where if you want like super live streaming really fast, then the quality is a little bit sacrificed. But since I'm going to be doing coding, I wanted you guys to be able to like see my screen, and hopefully this is a good trade-off. If not, I can always change the latency. I can't change it while I'm live, but all right. Cool. I'm just going to give everybody a few more minutes to kind of jump on the stream here before I jump in. This is going to be a little bit of a test, so curious to know, like, from feedback from you guys who can maybe just send me a message and let me know, can you see my screen? Can you see what I'm typing? Is it clear enough already? Is this too small? I can zoom in on some of the text to make it bigger or smaller, but I want to find a good balance between, what's too small, what's too big, because I'll do these again in the future, and we'll drill in on what is good for everybody. Right now I'm doing a 720p stream. I can probably crank it up a little bit. I don't know how powerful my computer is though. Yeah, so I'm going to be using Model Sim for some simulation stuff, and I'm just using a standard text editor for my writing of code, nothing too fancy, because I wanted to be able to like zoom in on it and make it look, legible for everybody watching at home. Or work, or wherever you might be. Clear enough. Okay, cool. Give me just 1 second. I will be right back. Okay, 17 people in the stream. That's cool. We'll see how many people end up jumping in. Have you tried using a workflow with Yosis in a Docker container? No, I have not, but I'm interested. I have used the Ice Storm toolchain on my Linux computer that I used to have. So yeah, I have some experience with it, and it's pretty smooth. But I want to do some more simulation stuff and less actual like FPGA building. So looking at waveforms and kind of describing, how I approach problems, FPGA workflow type stuff. So I'm gonna go ahead and get started here. Been 6 minutes, so hopefully enough people can jump in. And I'm probably not going to answer a ton of questions because I don't want to be like jumping back and forth to the chat. So if I don't get to your question, don't feel too badly about it. I'll pop in every now and then just to see if there's any things I'm not explaining well. But this is going to be focused on code, Verilog code, and simulation. Since I thought it'd be interesting just to see one particular approach for how you might skin a cat, so to speak. Just a disclaimer that this isn't always the best way. What I'm doing is not necessarily the best thing. There might be better solutions that out there. But this is something I think works well, if you're just kind of getting into FPGAs, how you might think about simulating a design and working through bugs and iterating some code. So I'll get started. So what I'm trying to do right now is I'm trying to create a wrapper for an I2C core. So, what I'm trying to do actually is create an I2C master. So I2C is a communication interface. Actually made a week ago, maybe, uploaded a video, what is I2C? If you are a Patreon person, you got early access to that. So, if you want to jump on my Patreon, support me there, that's great. You'll get early access to videos and things like that. Anyway, so as part of the Patreon, I'm wanting to create get more code out there and do more tutorials on some of these things. And I did SPI already, so that was kind of neat. And I wanted to tackle I2C next. Those are the two most common. UART, SPI, and I2C are the most common protocols to communicate with peripherals, external devices to an FPGA. So I think if you're not familiar with I2C, it's probably beyond the scope of this video. Like I said, I did an 18-minute video just last week on it. So if you're curious to learn the details, you should check it out there. But basically what I2C is, it's in a way to send and receive data from some off-chip device. So off of your FPGA, there might be, or a microcontroller too. There might be a device. Maybe it's like a analog digital converter, it's a temperature sensor, maybe it's a flash memory, things like that. And you might want to get some data off of it or write data to it. If it's memory, you might want to push some data off it, read some data from it. And I2C is one type of protocol that you might use to tackle that. SPI is another one. UART's more for communication back to a computer or to another device. If you read through the I2C specification, which I have done, it's pretty dense. Maybe it's worth bringing up. Let's see if I can download it. Okay. So it's freely available. Let me see if anybody's asking any questions or anything. Cool. So yeah, it's freely available spec. It's originally a protocol from Philips. Anyway, this most recent version is from 2014, but the original versions of this thing go back to 1982, just to show you how old we're dealing with here. This was before I was born. I2C spec version 1. Actually, the beta version, I guess. Version 1 was not till 1992. 10 years to go from beta to version 1. Holy crap. Anyway, if you read through this thing, it's 64 pages long. You'll figure out the details of I2C, how a master works, how a slave works, how devices get hooked up to it, blah, 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 blah. Originally, I was going to write my own core to kind of do all this stuff, to kind of do all these I2C stuff. And there's a lot of potential bugs in here, and I really wanted to write something that was pretty rock solid. So I ended up finding a core that I wanted to use. And there's a bunch of different cores out there, but the one that seemed like it had the most kind of traction on it that was freely available to me was one on OpenCores, opencores.org, which is kind of an old website. It's basically like if GitHub didn't exist and you wanted to make an SVN-based GitHub, OpenCore, and specifically for FPGAs, OpenCores is that. So if you go to projects, you can check out different types of cores, arithmetic cores, Cortex and multipliers and floating point thingies, communication processors, memory interfaces, soft processors that you can like build on your chip if you want to build a 16-bit microcontroller or whatever. It's really hard to sort through this because it's probably like 80% crap actually, and like 20% of it's actually pretty good. Maybe I'm being pessimistic. It might be better than that, but it's hard to know. So there's a few that are like starred. So some of them have like the star next to them. Here you go, an Ethernet 10GE Mac. This one's got a little star, so like it's open core certified, so maybe that's a good one. But you have to like make sure that you can use it because it's an LGPL is pretty forgivable. Anyway, I'm going off on tangent here, but I2C controller core. This one has a star next to it, and there's a bunch of other ones. Like, holy crap, look at this. 1, 2, 3, 4, whatever. There's at least 10 more here. This one's got a star though, so I was drawn to it and took a look at it and kind of sorted through it. The problem with this core, well, the good thing about this core is that it's tested and it's reliable. It seems like it's had been through a number of revisions. The problem with it, though, is it's a wishbone interface. So it's meant to really communicate to an interface called Wishbone, which is it's like an open source communication protocol meant to kind of talk back to a processor. So you might put a soft processor that has a Wishbone interface inside your FPGA, and then this core can talk to that processor using Wishbone. So the problem with Wishbone is I don't have a soft processor a lot of the time. So maybe I want to like use just normal FPGA kind of go, stop, start signals to talk to this core. Well, then you need to like, okay, so if you open up this core and you download it, so you can download the core. Oh boy, which I've already done. And if you read the document, this actually has a nice PDF that comes with it, which is great. So this is the core, this is the documentation for it. It's 18 pages, so it's less pages than the spec, which is good. And if you read through it, you'll see kind of how to interface to it. There's a bunch of registers that you can, here you go. So here's the registers, but these are like Wishbone registers. And I didn't really want to, talk to this core with these Wishbone registers. So the goal of this project is to basically abstract away all of these Wishbone registers and interface to this I2C core that I know is good using normal dedicated FPGA logic. And I wish my camera would stop kind of like bouncing, so I apologize, giving you guys probably a little roller coaster. Okay, maybe that's better. Do you see me still? Kind of. I'll slouch. I'm more comfortable that way anyway. Okay. Let's see if I can. Okay, is Wishbone like Axie? Axie is like Xilinx's. Yeah, kind of. It's like a simplified. Kind of, I guess. Yeah, it's similar in that it's a bus inside of an FPGA. I guess that's the similarities between Wishbone and Axie. So I don't have a Wishbone interface. I want to abstract away the Wishbone stuff, and I want to make this core work in a way that is kind of simple to use. So that's the key thing. I want to just make this simple. Like a lot of my I2C implementations, all it is just like, I want to write 1 byte to this address on this slave. Okay, no big deal. I want to read 1 byte from this address on this slave. Okay. I don't really care about like throughput or like crazy schemes where I have like multiple masters talking at the same time. I just want it to be pretty straightforward. So here is the core. Here's the I2C master that I'm trying to instantiate, and if you look at the top of it, I2C master top. This is the top of the core. So the order of instantiation is I2C master top, which instantiates a module called I2C master byte control, and I2C master byte control instantiates a module called bit control. So it's bit control at the lowest level, then byte control, then I2C master top. Now master top is where the Wishbone interface comes in. See all this like PRER, CTR, blah blah blah. This is all WB data O. This is all Wishbone stuff. And at the top level of I2C master top, you have all these Wishbone signals. Here you go. Here's your Wishbone interface. I don't want this. So this file needs to go away, and I'm going to replace I2C master top with my own version. And it's going to be called I2C master single byte. So single byte meaning I can read or write just 1 byte at a time, which again for my, most of I2C, maybe a lot of I2C, reading and writing a single byte is what most people kind of want to do. And so I figured let's make it simple to do. So it's a single byte interface. We have the I2C master byte control here, but we've abstracted away the wishbone stuff. I got started, and I know what I need to do. So I left myself this nice note here. This is where I stopped here. So if I try to compile this file, it fails. And here's what I need to do. So let me just show you where I'm at actually before I show you where I need to go from here. Comment this out so that it actually runs. I've been using ModelSim for this. ModelSim is freely available and easy to use. It's just what I got started with. Again, I'm not sure that ModelSim is like the best thing, but it's what I got started with and it's what I got comfortable with. So ModelSim's what I tend to use. ModelSim is a simulation tool for simulating VHDL and Verilog. So in your project, I have my I2C master single byte. This is the file I'm trying to test out. And I have a test bench as well, I2C master single byte TB. There's some other support files and other files that I'm compiling that aren't all necessarily used. You can always put them in the project. Whether or not they're used by the simulation is kind of up to the simulator. The tool will determine which files are needed. Inside, so once you compile it, you click Simulate, Start Simulation. You choose the library from which you are going to be running your design out of, which I'm just compiling everything to work right now. And you can run a simulation at any level, but the one that I want to run is my test bench. So that's I2C master single byte underscore TB. I kind of went through this quickly, so I'll do it again slowly. Here you go. So I'm going to simulate the test bench, click OK. That starts the simulation. It shows you kind of your hierarchy over here. So it shows you at the top I have I2C master single byte TB, which instantiates something called UUT, which is the unit under test. That's what I care about. And here's, again, the hierarchy. UUT instantiates byte controller instantiates bit controller. So that's kind of the hierarchy of modules. There's also an I2C slave, because this thing needs something to talk to. So the I2C device, the I2C device that it's talking to needs to be instantiated, which is just the slave module, which came with the core. Pretty handy. So I can talk to a fake, I2C slave that came with the core. Don't pay too much attention to objects or processes. I don't need those right now. The thing I do need is my wave. So this is where you'll see all your waveforms going in here. And usually what I'll do is, like, if I want to look at my UUT, I can right-click on it and click Add Wave, and that'll add all the files to the waveform. And then you can save your waveforms how you want them to look into a do file. And then you can do something like do wave.do, which I've already done. And here you go. Here's everything I'm interested in. I can get rid of this crap. So I've already added some waves. And you can do things like you can add like dividers and stuff, which is kind of nice. So you can say like byte core. And so everything between here is part of my byte core. And then add another divider here. Bit core, and here's the bit module. UUT obviously is my unit under test, but I'll add a divider there just to make it look pretty. Unit under test. Okay. And those are the files that I'm most interested in right now. So then I can save that format, and it'll save it to that wave.do file. Okay. You want to overwrite it? Heck yeah. Blow it away. Let's check in on the chat. You can pop out the chat so you can see it. That's a good tip. So many things you guys know about YouTube that I don't know. Pop out chat. Oh, look at that. But then you guys get to see your own chat. And I don't have another monitor that I can kind of toggle between. I'm going to pop in the chat. Go back in. No, I'm not. Where'd it go? Okay, well. Chat's here. Oh, restore chat. There we go. I'm gonna keep the chat in here, just in case I want to see stuff, which maybe I do. Okay, back to the wave. So, unit under test, byte control, bit control, boom. Let's click this little run arrow here to run the simulation. So this will run for, however much time you set it for. Right now I just have it set for 1 millisecond. It won't run for 1 millisecond, however, because at the end of my test bench, which is the file that I'm actually simulating, I have a $finish statement, which terminates the simulation. Or it'll ask if you want to terminate the simulation. Well, we'll see. Are you sure you want to finish? If I click yes here, it'll exit model sim, so don't click no. Then it kicks you back. Oh, so here's my test bench right here. I won't go through that just yet, but we can look at the waveform. So here is a waveform. Is this visible for you guys? This is actually kind of important. If this is too small, I can bump up the... Can I zoom? I can't really like zoom in on this. I can like zoom in like this, but vertically I can't zoom in. So I'm going to go ahead and ask you guys if this is visible or not. And if it's not, I'll bump my zoom on my display or something. In the meantime, I'll walk through what's happening here. There's some I2C traffic. So I2C is just these two signals. There's clock and data. So, and you'll notice a few things about I2C. I2C is white. It's got these white lines, these white dotted lines, which maybe you haven't seen that before, but that's a pull-up. So this is implying that this is not a one. It's not like being driven to a hard one. It's being pulled up to some value, to some high resistive value. So actually, in the signal type actually here is PU1. So that's the strength of the pull-up. Versus like ST1, which is like drive strength of 1, and it's actually driving and it's green. So this is pulled up high, so it is a high value. It does read as a 1, but it's not being driven on the line. Just because of the way I2C works, I2C is not being driven high, it's being pulled high, and you drive it low. So if you see here, when you actually are driving the line, it actually is a green and it's 0. So you're actually pulling the line towards ground. And I do explain this in the What is I2C video that I made last week. So check that out if you're confused about what I'm talking about. But the two signals involved, clock and data, there they are. And they're doing stuff. Let me check in and see if you guys can see this. Can you see this? I can see it. I'm on a phone. Okay, cool. Looks okay. Zoom a little bit. Please zoom. Looks good to me. Okay, well, some people say zoom, some people say it looks okay. Let me see, guys. Can I change this? I might not be able to change this maybe while I'm streaming. Oh, there we go. Whoa, there we go. That's pretty much as zoomed in as it's going to get. Okay, this is as zoomed in as it's going to get. And yeah, wow, I feel like I'm back in like 1995 here with this. Okay, I gotta get rid of some space. Okay, this is it. This is as good as it's gonna get. Clock and data. Where was I? Talking about clock and data. So this is just like one I2C transaction here. So clock is toggling, data is sending some stuff out. Cool. Things look like they're roughly working. Let's jump into the code now, because boy, I've been talking for a long time. I haven't written any damn code yet. All right, so what's going wrong here? What's going wrong right now is I'm trying to write the slave address to the I2C slave from my master, and then I'm trying to write some data. I'm basically here's what I'm trying to do. I'll show you. Okay, I'm trying to basically recreate in the spec for the I2C core. Here's an example of how to write 1 byte of data to a slave. So I'm trying to recreate this example to like see that I'm actually getting, hey, this waveform right here. Again, good spec. If you ever write a spec, including waveforms, so nice. Appreciate this dude a lot. So I'm trying to recreate this waveform. Well, I have clock, I have data in here, and I'm trying to make these look like these. So here's how to do it. You choose a slave address of 0x51, and you want to write 0xAC to that slave. So he tells you how to do it. You have to generate a start command. You have to write a slave address and set the write bit high. Then you need to receive and acknowledge from your slave. Then you need to write your data, receive and acknowledge from slave, and generate a stop command. So previously, I was doing most of these things, but I wasn't generating a stop command. So what ends up happening at the end of this transaction is the slave doesn't think that it's done, and it's waiting for something else. So I can't write anything else after this. This is the bug I encountered last time I was working with this. So you basically hang the slave, and it's confused. So what I need to do is I need to write a stop condition. Previously, so there's this input here to this core that says stop. And previously I'd assumed that stop was like stopping the middle of if you were in the middle of a transaction, you want to stop that transaction, you can set the stop bit. But reading through the core again and looking through the code, I realized stop is actually setting the stop condition of the I2C transaction. So at the end of the transaction, you need to say, I'm done now. And I wasn't doing that. So I have this command stop, which I have declared and not done anything with. So I need to do something with that. So first thing, it doesn't exist. So if you don't declare, if you just say our command stop like this, Verilog will actually interpret this as a wire of width 1, which is really nice of it. And also mean, because I can't tell you how many times I've mistyped a signal, and then it's like, why are you sending a 16-bit value to a 1-bit wide signal? I'm like, why is my thing 1-bit wide? I'm like, oh, it's STP, it's not stop. If you have a signal called rcommand stop and rcommand STP, the tools are like, yep, those are totally different. And I'm just gonna I assume you meant to do that. Verilog lets you hang yourself so easily, which is nice sometimes, but you can get into trouble. So always declare stuff. So even my 1-bit wide wires, I didn't have to declare w command start right here. It would have declared this it would have just inferred this is as a 1-bit wire, but I like to declare everything. So yeah, I don't know. I learned VHDL first, which would have just puked all over the place if you didn't declare something. So I need to declare my stop. I'm going to declare it as a reg. Rcommand stop. And now it's an input to this module, and I'll use it to set the end of the command. So now I have that available. That's handy. What notes did I leave myself here? Need to implement start stop bit generation. Previously assumed the stop input to the core was never used. However, this is a critical signal to set the STO bit inside the control reg. This module should automatically be handling start and stop bits. Writing to the slave address, create a state machine here to drive a write transaction correctly. Yes, state machine. Okay, this is good. So I will show you guys how to create a state machine inside of Verilog. I'm going to keep this note in case I need to refer back to it. So there's a couple different thoughts. I haven't actually done a video on how to create a state machine yet in Verilog or VHDL, but I feel strongly about it. And there's two methods. There's one that's it's next state, previous state thing. You guys know what I'm talking about? Next state, previous state. I don't like next state, previous state. It's confusing as shit, and I never felt comfortable with it. It doesn't make sense logically, and the tools don't care which way you write your state machines. That used to be the case, that you had to be really careful about separating your combinational and your sequential logic back in 1995. So these rules, if you look online of how to write a state machine, you'll find things you have to write it in this way, because at one point that was true, but the tools got a lot better, and you don't have to. They're smarter at interpreting what you meant. So I like to write my state machines in a single process, because I just think it's more human readable. So I'm going to do that. So if I reset, and I usually call my state machines R SM main, and if I'm in reset, I'm going to send it back to idle mode. And I haven't really figured out what else I'm going to do just yet. Otherwise, it's a rising edge of my clock. So here's my asynchronous reset condition, and otherwise I'm in a synchronous clock area. So switch case RSM main. Ooh, I've been writing C for too long. Sorry. Let me refer to my own damn web page. Okay. Yeah, right. Case, parentheses, got it. Okay, good. Thanks, Russell, from previous days. Okay. Idle. And I usually put begin and end around my. Did I do that right? Parentheses. Yeah. Okay. I'll just leave that open in case I need it again. All right. So I'm in idle. So if you're sitting here in idle, that means that you're about to start a transaction. If I want to start a transaction, then what's the first thing that happens? So my interface to the top of this module, which I didn't really show what it looks like. It looks like this. So here's my interface. I want to make it simple. I want to pass. Before I talked about this, let's see. Check on you guys in the chat. How we doing? Okay. So, all right. So I have a clock, a reset, and an enable. This is just like an enable for the core. You can just leave it enabled all the time. Slave address. This is the slave address you want to write to. This is a write start pulse that kicks off a write transaction. This is what's going to start our state machine from doing stuff. There's also a read start, which will also start our state machine, but we can only access one or the other. They're mutually exclusive. This is the data we want to write. If it's a write transaction. We're going to drive some busy signal just to indicate to whoever is upstream that like we're in the process of doing something. So as soon as we're in idle and we see this write start or read start, we're going to drive busy high, and we're going to keep it high until the transaction is complete. If we read something, we're going to populate this read byte here. And then we have this possible error condition, which I haven't figured out if I'm actually going to use or not. But if something goes wrong, you can potentially drive this error to tell somebody upstream what's going wrong. So this is pretty much, the crux of this whole thing. It's just like, how do you drive these signals in an appropriate way to drive I2C transactions? And again, like I really want to make this simple so that if anybody wants to write anything, like get data off a temperature sensor. Okay, I need to write a slave address, pulse this thing, and that's it. Kick off the address you want to. I guess I'm going to need to kick off. I might need to add a read address if I want to read something from the thing. I haven't gotten there yet. Let's do writes first. That's what I'm working on. Again, trying to recreate this writing 1 byte of data to a slave thing. So right now, that's all I care about. I'm going to focus on that. I like to break up problems like that, like work on something meaningful, get something working, even if you know that like I'm going to get writes working first and then I'm going to get reads working after that. Don't try to get them both done at the exact same time because it's probably a little bit overwhelming, and you can write, maybe you won't write the best code. I was driving busy here previously because I was not using a state machine, but my state machine is basically going to do all this busy stuff. So that's gone. Blow that away. All right, so I'm in idle. I'm sitting here and I'm waiting. This core is just waiting for somebody to come along and do something. So again, I write start is going to be the thing that kicks things off. And if that happens, then I'm going to, first of all, set busy to 1. So busy goes high immediately. And am I using this signal anywhere else? Okay. This also kicks off into the core a write start, but I kind of want to have control over this. So I'm going to change these to that, and I'm going to change this. This is something I like to do. This is why I like to use like I underscore and O underscore in the module names, because a lot of times I want to like register internally these signals. So if they change at the high level, I don't necessarily see that change internal my module. It's just a way to like make it safe, so that you don't have to rely on somebody upstream like keeping the value the way you want it to be. You can just see the pulse and then go. You'll see what I'm talking about. So our write start, I want that. Read start, I want that. And I also want to create a registered version of the data that I want to write. Write byte. Is that what I called it? I think so. Yeah, write byte. So if I get a start, I'm going to register. I can just do this, or I can do that. Those are the same thing. But to be clear, do that. So since I've been assigning some signals in the sequential part of the always block, I like to add them to the reset condition. And I'm anal about aligning things. That's important. And then I need my state machine to actually get out of this state and do something slightly more interesting. So state machine main is going to go to slave send slave address. These don't exist yet. Idle, send slave address. I need to create parameters for those. So that's probably good. Send slave address case. So when I'm in send slave, so again, this is how I like to do state machines, right? You're sitting here, you're in idle. If this happens, go here. Next clock cycle through, you'll be in this state, you'll do this stuff. It's just easy to see the flow, like the transitions of things, and like what happens when when I write start goes high. Well, I register this. Oh, you know what? Actually, I'm going to register the data that I want to write. This one actually does require the input data. So again, this is like, if someone kicks off a write transaction, I'm going to register the byte that they want to write immediately. Actually, you know what? I think, yeah, this is the problem I was having. Okay. So the first byte that I want to write, I need one more signal. So I want to register, I need a better name for this signal, this is bothering me. But I want to register the input byte that they want to write on the transaction into some local storage, but the data that's actually going to be written to the slave is going to be the slave address, which I believe, actually, you know what? I think I put that in an input to this module. Is that true? Yes. So slave address is going to be an input to this module. And the way this core works is if you want to write, if it's a write transaction, okay, let me review this actually. If it's a write transaction, the write bit needs to be set, which I believe, let me see if I can find it. Okay. So it's the last, so here's like, if you want to set your slave address. So the first byte that goes across on the transaction is your slave address, which is 7 down to 1. So it's a 7-bit address. And then your read/write bit is your last bit that gets sent. Is it read 0, write 1, or write 1, read 0? Okay, here you go. Writing to a slave is 0, reading from a slave is 1. So, yeah. That's what I'm trying to recreate. So I'm going to write iSlave address, which, as you noticed, was 6 down to 0. So I'm writing a 7-bit wide address to an 8-bit wide signal, R write byte, which is here. So R write byte is getting something that's only 7 bits wide, and so I need to basically append the fact that it is going to be a write transaction, which is going to be a concatenation operation. So concatenation in Verilog uses brackets. Untick B0. I could be more clever, like write command. And yeah, you know what? Let's not get clever here. Let's keep this simple. Otherwise, you're going around the file. If you're only using it as one spot, you know, maybe if I use like write command in a bunch of different spots, I turn it into a parameter. But since it's just in one spot, you know, this is fine. This doesn't bother me too much. One tick B0 equals write command. You just have it in the comment right there. So this is the first thing that's going to be written. Is going to be the slave address. And then I'll go to like wait slave address, which is like wait for it to be done. That's probably a better name. And I do still need to register this write byte, and this signal name is still bothering me. Alright, data. Is that better? That's less better. Let's call it byte reg. I guess. I don't love the signal name. This is bothering me. Like the smallest things like signal names bother me. But maybe it's just me. I gotta get them right, otherwise it doesn't make sense when I read it later. I'm like, what is this stupid name? So I have write byte and R data reg. Is that what I called it? I don't remember what I called it. See, it's a bad name. Byte reg. Okay, this is stupid. I'm gonna fix that. I'm gonna call it something better eventually. All right, this is the data I want to write, but I'm not going to be able to write this data until the next SPI transaction. Sorry, I2C. What core am I doing? I2C. So I'm not going to be able to write this until the next transaction. So I'm going to wait until this is done. Now, when this is done when busy, which is an output of the core, goes low. So busy is conveniently provided. Is it convenient? Oh, I'm generating busy. I was generating busy. Ooh, I commented out the busy code. Okay. Looks like, let's see. Now I need, so I did something too prematurely. How do I know when busy is done? Okay, what can I look at here? So the question is, what can I look at inside the byte controller to know that the transaction is in progress? I think I can look for the falling edge of command ACK, I believe, is a good one. Yeah, that looks pretty good. Command ACK. Let's go with that. So I'm going to look for a falling edge of command ACK, and if that's not right, I can change it. But in order to look for a falling edge, hey, this is another fun thing. How are we doing? End case. Yeah, I do need an end case eventually. Hello, Robert. Hello, everybody. I will need an end case. Thank you for the reminder. I'll put that in here. There you go. These should all be like indented a little bit too, probably. Okay. So, oh, how to look for a falling edge? Yes, falling edges are important. So if you're looking for a condition, so like what I'm basically looking for here is I'm going to kick off this transaction. It's going to write all this data out, and then I'm going to look for the falling edge of command ACK, because command ACK's really low for a long time, and then it just pulses. Oop, not over there. Here. It pulses for literally just one clock cycle. So here's command ACK. This is the one I care about. And it's only one clock cycle wide. So I'm looking for this one little teeny falling edge here. And if you're looking for a one clock cycle wide falling edge, I shall show you how to do it. So command ACK is this wire coming out of the slave, which I don't currently use. Nope, I don't use. So what I like to do is create a registered version of the wire. So I have one called W command ACK, which is the wire. That's like the now version of the ACK. And then R command ACK, which is the registered version of the ACK, which is the one clock cycle delayed version. And I'll just create cat another always block to do that. Purpose of this always block. I always like to define the purpose of an always block because always blocks should be created with purpose. Create 1 clock cycle delay to detect falling edge of command ACK, command ACK from core. Assume this is when command is done. So always at pause edge, iClock, in end. So you'll notice this one I'm not using a reset for. If you don't need to reset a signal inside of an always block, don't do it. Save resources. Resetting signals, well, it depends on the FPGA, but like Xilinx chips, for example, Altera, Intel chips now, you know, they have a lot of routing resources available, and like a huge amount of routing resources gets eaten up by resets. I read an interesting white paper a while back that basically said, if you know, written by Xilinx, if you don't need to use an asynchronous reset, don't use them, or any reset. In this case, I don't need to reset the signal. I can just do R command ACK gets W command ACK like that. That's it. Because like, what am I going to reset this damn thing to? 0? Okay, whatever. If I just wait 1 clock cycle, it'll be back to what it was. It'll just be the delayed version of this. Like as soon as the clock starts ticking. So, yeah, don't reset signals that you don't need to reset. I think that's a good lesson. So when I'm waiting for the slave address here, I'm waiting for done when command ACK goes low. When command ACK has falling edge is more precise. So a falling edge is when the current value is 0 and the previous value is 1. So if it goes from a 1 to a 0, that's a falling edge. So that happens, when that happens, I want to know about it. So if R command ACK is a 1 and not W command ACK, then do something, and the thing is going to be get out of this state first of all, because we're done. So I'm going to create another state called like send. Let's assume we're just doing writes. Again, I'm probably going to change this when I do reads, but let's just assume we're sending writes, so send write data. And I'm going to create another state. And I like to space this out. And maybe give it a little description. Wait for command ACK from core to know slave address is written. And I'm not trying to handle any errors or any weirdness right now. I'm kind of assuming that like everything's going to work perfectly fine for the first go around, and then I'll add in like the corner cases and weird gotchas later on. I think this is, generally speaking, a good approach. And all this is doing is just waiting for this condition. So you're just sitting here spinning. This is just going to spin, 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 spin for a super long time, like hundreds and hundreds of clock cycles, just looking for this one condition. Is command ACK and not command ACK? Is command ACK and not command ACK? Okay, and then eventually it happens, boom, happens, and you get out. And that's it. That's all this state's good for. And I like to keep my states kind of like clean. You know, don't try to do too much in one state. Like the nice thing about a state machine is like, you know, you can see the enumeration of the states. So you can see the traversing. Like I'm in idle. Okay, now I'm in this. Now I'm in this. And in your simulation environments, you can actually better debug the flow of everything. So I really like to kind of, how many extra resources does it take to create another state? Like a register and like a couple LUTs. You know, at that point, for the ease of readability, it's well worth the trade-off of resources, in my opinion. You're never going to bump. I haven't bumped up against resource utilization problems where I care about whether or not I have too many states in my state machine, ever. So, yeah, if you do, I'm sorry. R command ACK, and so just to explain this falling edge thing just a little bit. So I'm looking for when this condition is true. When R command ACK, I need both of these things to be true in order for this to execute. So if this is a 1 and the inverted value of this, so I'm basically looking for when this is a 1, this is a 0. but I want it to be a 1 for this if statement to evaluate to true. So I need to invert it. This is the bitwise inversion, and then and them together. So this becomes a 1, that's a 1, this is true, boom, done. Okay. Then this at this point I know that the slave address is written, and then I want to send the write data. Send the data to write to the slave. Cool, cool, cool. Send write data. Begin and so this is where I'm actually going to send. So okay, just to review, I'm trying to recreate. I'm trying to recreate this programming example here from this I2C core. Just to people who haven't maybe been here since the beginning, I have an I2C core. I'm trying to rewrite the top level of the I2C core to my own likings and recreate what's going on in the core by modifying this example. I'm abstracting away something called the wishbone interface, and I'm creating my own interface to talk to this core. I'm trying to write 0xAC to some I2C slave at address 51. And here's the instructions of the core on how to do it, and I'm just trying to recreate these instructions. So far I've generated the start command. Have I done that? I did that here. That's what that is. I have written the slave address and the write bit. So that's slave address and the write bit. That's this. That goes into this write byte signal. And then now I'm here receiving an acknowledge from the slave. That's this command back. This is the acknowledge from the slave. Then I write the data. So I'm on step 4. Write the data. So now I need to replace, you know what? I'm going to, here's another trick. Okay, I only want write start to be high for 1 clock cycle in my case, and the only time I ever want it to be high is when I well, let me rephrase that. I only want write start to be high when I want it to be high, and I want it to be low almost all the other times. So you can do something called default assignments, which I find very handy. This is basically like Verilog will basically treat these. I'll do it. Rel write start 1 tick B0. I really like to do this. It's a really handy trick and hasn't failed me yet. So what happens here is by default, Verilog will assume that write start's going to be low. If it ever encounters a situation in which it is not low elsewhere further down the code, then it will use that. So here, for example, write start is set to 1. So this will override this because it came later in the code. They're all executing at the same time, but it's the synthesis tools that will be like, oh, this has a higher priority. So this is actually like an if-else chain. Like if I'm in this state and write start is true, then set it to 1, else, set it to 0. It's just an easy way to like capture that else without having to like assign in every single state the fact that write start is 0, which I've done in the past, but it just gets overwhelming. For every single signal you have, if you have to assign every signal in every state, your state machine just goes and gets huge. So if you set these default assignments in the beginning, you can actually cut down on the number of signals that are only being assigned. The ones that are being assigned are the ones you actually care about, which is nice. Like busy though, I actually do, there's a difference. Busy, I actually want it to be a 1 throughout the entire time that the slave core, that this master core single byte state machine is not idle, and it's only idle. It's only I can do this. To be explicit, I'll just do this. Else busy gets 1 tick B0. So busy is low if I'm in idle and nothing's happening. Just to tell the higher level module, like, yeah, go ahead, jam some data into me. So busy is a little bit different, but write start is a pulse, so I want it to be most of the time low. Handy trick. Okay, and then down here, I want to start it again. This is a new pulse, and I want the write byte to now be my R byte reg signal, which is right here. So I've registered the data that the user wanted me to write, and I'm kind of just, this is just sitting on this register is just waiting for its time to shine. It's not doing anything in this state. It's just kind of chilling, and then, oh, here we go. I'm ready to go. And you register, oops, this should be a 1. And you register your registered version into the data that you want to write. So this write byte goes into the core. That's this one right here. So this is your data in. This is the actual data. So this will be your AC in this slave example here. And do I need to do anything else? I think that's it. And then I'm going to go to a new state. Do one thing and then get out. And I'm going to go to wait, write data. Wait for the slave to acknowledge the write. Oh, one other thing I need to, okay, well, I'll do this first. Wait, write data. And this is going to be the same thing here. So I'll just copy this. You could like send these to the same like wait state if you wanted to, but then you'd have to have different decode logic about where to go next in the state machine. Nobody likes that. So again, create another state. Who cares? Not that much more resources. Even though these two wait write data and wait slave address look very similar, I just think it's easier to follow the flow like as a human. So it's worth the resource trade-off. I'm gonna do I usually have like a cleanup state, whether or not you need it. 1 clock cycle for cleanup. Clean up, everybody do share. Okay, and then RSM main just goes straight back to idle. Because why not? Sometimes cleanup is nice to like just give you an extra clock cycle for things to reset. And just to make sure that you're traversing your state machine correctly, I don't know, I put it in there. I say I use it maybe 25% of the time, but it's just like a habit that I end up doing. Let's see, do I need anything else here? I think that'll, yes. Okay. This actually is not write start now that I'm thinking about it. This is write. Hang on. Oh, okay. This is command start. I'm confusing myself a little bit. Okay. So this is history stuff. So I previously had something called W command start, which I don't want to use anymore, so I'm going to get rid of it. I'm going to call it command start, or the registered version of command start. I'm going to blow away this old assignment here. And this should actually be our command start goes to 1. Oops. So read and write both use the same start to start the transaction. This just starts a transaction, and then command stop indicates the last thing is done, and so that the master will drive an I2C stop condition on the bus. I was confusing myself a little bit. This is really like write command and read command. So these are like indicators to the core to be like, this is going to be a read command, this is going to be a write command. And then I was also confusing myself because why? Was I? No, I think I still need, okay. The thing I'm wondering is, do I need to write into the write byte the actual, when I'm writing the slave address, do I need to include the LSB like I was doing down here? And I'm not sure if I need to do that. I'm also going to change this from write byte to command byte, because this is just the data that's going in. It can be a read command, it can be a write command, it can be anything. So that, you know what that means? That means this becomes write command byte, and this becomes write byte, which makes me happier, because that's actually a name that makes sense. Okay. This is good. So where was I registering that? Okay, this is actually going to be our write byte command start, which is a better name. So this is the write byte, and this is the command byte. Command byte. Yes. Okay. Yes, it's all coming together. Okay. Command byte is now the first time going to be my slave address and one tick B0 indicating that it's a write command. I also have, I'm also registering the data that I want to write on the next time through the state machine, which is going to be down here. That I'm going to use that. And this is now going to be our write byte. I'm going to pull that out. And this is going to be, I'm going to be writing the command byte. Not the write byte, the command byte. And this is command start. Now, so command start needs a default assignment. Up there. Bippity boppity. Command start. Get started. Do I need write start still? I don't think I need write start. Actually, that kind of goes away. Unless, oh no, it becomes write command. That's fine. So the only thing I don't understand is why these two extra signals are here, if I need these or not. That's more of a core thing. I'm not totally sure, but I do. Okay, so now I have write command and read command. So that means this is write command, indicating that it's a write command. Actually, I'm just going to go ahead and get rid of that. And, oops, our write command. So if it's a write command, I'm going to say that goes to 1. By default, I want read command going to 0 and write command going to 0 as well. So by default, those are just going to be sitting at 0, and then if it's a write command, this will go high. And it'll stay high for the entire transaction, kind of like busy. Busy will stay high for the entire transaction as well. And now command start is the only one I'm assigning by default. Yes, this looks better. You know what? I haven't checked in on you guys for a while. How are we doing? If W command DAC is more than 1 clock cycle wide, can I still use that method to detect a falling edge? Yes. Absolutely, Carlos. It works no matter what. How many people are here? 30 people? Cool. Okay. Hey, quick but shameless plug. If you're enjoying this, please check out my Patreon, patreon.com/Nandland. Patreon.com/Nandland. And support me here, please. Because the more people that support me here, like the more motivation I have to do cool shit like this. And these things will happen more often. So if you are a supporter of me on Patreon, super appreciate all you guys sticking with me. Trying to just keep the content cranking out as much as I possibly can get it out to you guys. And more supporters will help my motivation go up higher. So help me out. Appreciate it. Okay, back to the code. Idle, wait slave address, send write data, wait write data, clean up idle. I think we're in a pretty good shape at this point. I definitely have some errors. For example, I never declared this signal. So let me do that. I got some states to declare too. So what kind of states did I make? So first of all, how many states did I make? This is the annoying thing. VHDL does this a little bit better. I like the way VHDL can do state machines because you can declare your own user-defined type and then it will automatically enumerate them in order. Verilog, no such luck, at least not that I know of. So I have to manually declare idle. Wait slave address is 2, send write data is 3, wait write data is 4, cleanup is 5. So I have at least 5 states, which means I have a 3-bit. I need at least 3 bits to indicate 5. 3 bits gets you up to 8 values. 2 to the third is 8. So local param 2 down to 0. Let's call it idle equals 3 tick b 0 0 0. And then how many did I say? 5? Yeah. So let's count. 1, 2, 3, 4. That's not 4. That's 4. I know the last date was cleanup. I know there was a wait slave address. That was probably 1. Is that the second one? Yes. Wait slave address, send write data, wait write data. Send write data, wait write data. And because I am anal about these things, those equal signs need to be aligned. They must be aligned. And I have like a Emacs thing that allows me to align those things. But I'm not using Emacs right now. Okay. Idle, wait slave address, send write data, wait write data, cleanup. Good, 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 good. I also need the state machine. That's important. I'm going to combine some of these things just because too many lines. I used to be really, like VHDL, I was really picky about declaring everything on one line. Each signal gets its own line in VHDL in my rules. It used to be that way. I've gotten less picky about that because honestly, like, it's such a killer white space. So let's just put the regs on the same line. And that cleans things up a little bit. I could combine these, but that's fine. And then I need one more reg for my state machine, which is going to be, since there's 5 states, 3-bit wide, 2 down to 0. RSM main. There we go. State machine's declared, so that won't have an error, which is good. Idle. What am I forgetting here? Anything? I think this is perfect. I think I did the whole thing perfectly the first try. I'm just kidding. This has probably a lot of bugs in it, which maybe you guys found some already. Let's find them together. Here's the fun part. The bug finding. Okay, so first of all, model sim, where are you? Boy, I thought we'd be here sooner. Okay, it's already 9:40. Oof. That's fine. Let's compile this. It failed with an error. Shocking. Not shocking. Undefined variable write start. Indeed. Write start. Oop. Oh, R write start. It's a register. Okay. Do I even use this anymore? Nope. This was changed to command start. And that makes these not aligned anymore. Okay, so command start. That used to be write start, but I got rid of it. Command start's a better name. I should also probably just... Those are the only ones I really care about. Command start's important because command start kicks things off into the core. The other ones I'm not going to reset because, like, I could reset R write command here. Like, I could do this. But I'm not gonna, because again, saving routing resources by not resetting signals you don't necessarily need to reset. And also, the core won't use this unless the command's already started. And guess what? I'm restarting our command start. So, whoop, it's gone. Let's see what we got. Compile. Oh my god, that was it? That's pretty good. Oh, here's a little shortcut. If you want to, so if you recompile everything and you don't crash your simulation or whatever, everything's green, check marks, successful compilation. I need to change my test bench, but then you can just click the little up arrow to restart your simulation, and it's all hunky-dory. I need to change my test bench just a teeny little bit. Oh, here's my test bench is yucky. Let me look at it over here. Okay, so I had a test bench before that was like doing too much stuff. So it was like doing write 1 byte of data to the slaves. That's the slave address. And then waiting for busy. And then when busy went low, writing the data. Ain't nobody got time for that. So let's blow that away. Like that. And instead, I'm going to be just doing R write start gets 1 tick B1. This is the new interface that I just created. So this is better. This is much better because I got that nice state machine that's going to do all this work. This was basically me testing out the core without the state machine involved at the test bench level, like making sure that I could exercise the core. I did this a few days ago. And I kind of got a good feeling for how the core worked. So I was like, you know what? This deserves a state machine. Rather than force the user to do all this brutal stuff, right? If you were instantiating the single byte core and you had to manually do all this every single time you wanted to write a byte, you would never use my fantastic core at all. Instead, you want to do like nothing. So let's check this out. Write start, set that 1, and then byte. 8-tick HAC. So this is hex AC, and that's friggin' it, yo. That's it. That's all you need to do. How sexy is this? This is great. And I'm just gonna make the clock cycle go low. Start it. This is the data that I want to send, AC, and set start bit low after 1 clock cycle. So that's it. Much better than all this garbage up here where I was like waiting for busy, spinning for a long time, blah, 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 writing the data, blah, blah, blah. And, you had to know the slave address because it wasn't automatically taking care of that. Now, this core does all that for you. It writes the slave address for you. It writes the write command for you. It waits for the slave address to be done. And then it sets the data that you actually want to send, starts the command off, and then does a little cleanup state and sets the stop bit. Ooh. 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 Haha. That should be that. This rubber ducky debug stuff is great. I'm finding all sorts of bugs in my code just by explaining it again to you guys. This is going to be my new way of I'm just going to work 8 hours a day like this. So the reason that's a problem is because the command start is the start of the transaction. Command stop is the end of the transaction. So what I really wanted to do is starting the transaction is the slave address. Ending the transaction is the actual data that I'm writing. I wanted stop instead of start. That's good. Good find. It's a good find. This one though, if I set it to 1 here, it'll stay 1 forever. That's not what I want at all. I want it to be 1 for 1 clock cycle. So again, bam, default assignment time. Let's go. 1 tick B0. So again, this is a default assignment for the entire case statement. If it hits this, it'll set it to 0. If it hits anything else anywhere else further down this state machine, that'll supersede. So here it is. This will supersede. It'll set it to 1 for 1 clock cycle. Yeah. Now this will definitely work the first time. I'm gonna ignore that. I need to recompile those two things, so they're good. I need to go to my waveform, restart, and keep everything that it was. And fingers crossed. Oh, something's happening. Too much something. This looks like too much something. But that's okay. It's doing stuff. I also added a whole bunch of signals to my unit under test, so I'm actually going to blow away. So because I created a bunch of signals, ModelSim doesn't know about them because they're not in my wave.do file. And I need to add them to my wave.do file, so I'm going to blow these away by deleting them. And I can add the updated version back in by going to my simulation, UUT, And you can see the objects here. So this is like, oh boy. So these are all the things inside my module. Here's my local parameters that I created, clocks and various signals and everything. I want all of it. So right click on it, add wave. And that will add them all to the bottom. If they're all selected, you can just boop-a-doop, 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 boo, drag them back up to where I wanted them to be, which is right there. And here's my new ones down here. So like command, start, stop. These are new signals that I just created that didn't exist last time I ran the simulation. So there's no data for it. It doesn't record data that's not, by default, you can make it do this, but by default, ModelSim won't record data for waves that are not on your waveform. There is a way to override that and make it record all data for all waves, even if they're not being captured on your waveform, which is nice if you have really large simulations and you don't know what you want to look at. You're like, I have no freaking clue. I want to look at all of it. Or I might want to like add this signal and then remove it, or add this group of signals and remove those. And rerunning your waveform, rerunning your simulation might take a super long time. Like I've had simulations that take like literally overnight, and coming in the next morning and being like, okay, what might I want to look at today? And like be like, oh, I didn't record that last night. Oh well, let me write another one. That's awful. So I've recorded everything, which blows up your waveform file quite a bit. Like I've had multi-gigabyte waveform files, but trade-offs. This is fast enough that I can just click boop 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 boop, and bam, I got my data. So this didn't exist and now it's here. I also changed my wave.do file, so I'm going to go ahead and save it. Wave.do. Do I want to overwrite? Yes, I do. Bippity boppity. All right, the debug continues, but in the meantime, let's check in on you fine folks. How we doing? 32 people. Okay. Loving this. What's up, null object? I'm loving you, man. How about implementing an 8051? Someday. You can declare enums in system Verilog. yeah, okay. System Verilog, I agree, has some nice features that I would like to. I didn't want to really like broach the system Verilog thing because that's a whole other subject. I use system Verilog for my test benches most of the time. Hopefully you can do a live stream answering questions. Electromatic, yeah, I did that last time, and I'll do that again, I'm sure. I keep my states as numbers. It seems less confusing because 2 happens before 3. You can do that. Yeah, I kind of like to see like the enumeration. I don't know, like this is a VHDL thing. Like I like to enumerate my states just when you're reading it and you understand. But yeah, I can see like a 2, 3 thing. Working out for you, Doug Smith. What's up, man? Hey, kiss my W. Sounds good. I'm not sure what you're responding to, but it does sound good, doesn't it? It does. Okay. A couple things. I like to. So here's how you can enumerate your. Blam. There you go. You get your 1, 2, 3 things. So now things happening. You can change your radix in the waveform viewer, so you can make sure that your state progression makes sense. In VHDL, you can actually see the enumerated. You can actually enumerate these and then see on the waveform like idle, waiting for this, cleanup, whatever. I really miss that. I really wish I could do that in Verilog, but as far as I know, you can't. Maybe System Verilog you can, but I'm not doing that right now. So I'm also going to cast these as hex because those are datas that I'm writing and care about. What else? Read byte. I don't really care about that too much. I'm going to make these hex as well. And I'm going to save my format again so I don't lose those changes. Okay. Let's check. So, waveforms, whenever you're debugging, solve the first problem first. Like, don't start at the end and work your way backwards. This is time, right? Time is at the beginning. Here's the beginning. Everything is happy at the beginning. You know why everything's happy at the beginning? Because the very first thing that happens is I'm in reset, and everything works perfectly. And then the clock starts and things go to shit. But eventually, you hope that you can work your bugs out. But as soon as this clock starts toggling, it's like, okay, is stuff working correctly? Are things happening the way I want them to happen? Let's dig in and find out. So the first thing I notice is I'm registering A2. Okay, so R command byte is my registered version of the data that I want to write. So my write byte is A6. A2C, but my command byte is, oh, my R byte. Okay, there's my registered version, A2C right there. A2 is my command byte, so that's going to be my slave address, 51, with the right bit low, which I believe is correct. Let me just double check my test bench here. This should be this. I had A2 written here because it's a shift by 1, right bit low, which A2. Hey, look at that. Okay, I can do stuff. So A2 is the first command that goes in. That looks correct. That's indicating that I want to write to address 51 slave and that it's a write transaction that's coming. So here's my acknowledge from the slave. This right here. So okay, so just real quick, I'll back up. Here's where the slave, this is SM main. So this is my state machine sitting here at 0, which is idle. It goes to 1, which is the beginning of the write trend. I'm sorry, what did I call it? Wait slave address state. So 1 is wait slave address. So this is waiting for the act to go along. So I'm just spinning for hundreds of clock cycles while the I2C bus is active, which is good. The I2C bus is ticking. You know, there's my clock, my data, it's sending stuff, and we can actually look. It's kind of hard to see on this thing, but this waveform here, like there's my 8 clock pulses, and then there's my clock pulses. It looks like you have, so look at SDA down here. So you have 8 clock pulses here for this first command sequence. You have a high, a low, a high. That's my SDA. So high, low, high, good. Then it looks like I have 2 lows in a row. 1, 2, 3 lows. 1, 2, 3 actually. Yeah, 1, 2, yeah, 3. There's 3 there. And then it goes high for 1 clock cycle. That's that. And then it goes low. And low again. Low, low. Boom. End of the transaction. And then I'm done. So the slave address is being written correctly. I have verified now, like visually verified. This isn't like formal verification or anything. But visually, this looks good. You went out. All right, great. Next, my state machine goes to state 2, and it's there for just 1 clock cycle. Because when I'm in state 3, I'm looking for that condition, that magical falling edge condition. When W, oh crap, what did I click on? Okay. W command ACK and R command ACK, which if you put them together, woohoo, look at that. The W command ACK is low and R command ACK is high. So that is my trigger. That is my falling edge trigger that tells me that the command has been acknowledged by the core and I can do shit. And what I'm going to do is, that's this. So R command ACK and not W command ACK. Cool. Then all I'm doing is transitioning states. So going to send data. And what I'm going to be doing is sending command stop, which is the stop, requesting the stop transaction. I'm going to be sending AC, which is the data that I want to write. And it's a write command, so I'm just keeping that held high. And I'm going to be waiting for the response from the slave. So let's proceed forward in time. You know, we can look at the waveform too, actually, make sure the waveform looks good. Something doesn't look right, but I'm not there yet. So here's the beginning of the byte. So it's high for 2 pulses. Oh, that looks a little different. That looks a little different. But maybe not. It's kind of hard to tell. That might actually just be 1 and like a little bit. Yeah, that could just be 1 pulse. Because it goes low here and it's high here. I think this is just the first pulse. And then it's low and then it's high. So high, low, high. And then it's low, high, low, high, low. Oop, this doesn't look right. Low. And then it goes high. Interesting. Interesting. Mine goes high, low, high. And then it definitely goes low, low, low for 3 clock cycles. and then high, low again. This one goes high, low, high, low, high, high, low, low, low. So why am I sending the wrong data? This does not look correct. So this is the first problem, which is not bad. I mean, I made it all the way to the second byte. That's okay. Before I found a problem. So my command byte is AC. Let me see. So command byte is the data that's being loaded into here. My data in. It's still a write command, I believe. And this is me thinking. The only difference that I had here is that I'm now sending a stop versus before I was sending a start twice. So I set a start, I wrote A2, set start low, I wrote the byte to AC, I hit start again. Now I'm hitting stop. Maybe that's the difference. Not sure exactly. But it's low here, high, low. And the other thing that's confusing to me is I wouldn't have thought that this would continue because I should be sending a stop command. So am I not sending a stop command here? Let's see. Command stop. Default is 1 tick B0. Send write data 1 tick B1. Oh, well, so why am I going, okay, so I do have a question, which is why when I am right here am I still doing stuff? Because this goes, I'm not like triggering anything in the core. These are both low. I feel like I might be misunderstanding something about this here. Let's see. Set the right bit. I think I am setting the right bit still, aren't I? Yeah, the right bit's still set. AC to transmit, set the stop bit. Wait for this, should be 0. This whole command sequence kind of looks like this. 1, 0, 1. 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0. 1, 0, 0. 1, 0, and then it goes high here. And then it goes high, low, high, low, high, low, high, low, high, high, high. I wonder if this is actually the data that I'm writing out here. And I'm stopping this too soon. So let me add a little bit more delay to this just to see what would have happened further on. Because I didn't quite give this a chance to finish. So I want to give it a little bit more time to see what would have happened further out in time. So recompile, restart, okay, waveform, run. Okay, yes, so I'm definitely doing something wrong driving the slave because it looks like what I intended to do was just have 2 bytes, like here's my slave address, boom, here's my write data, boom, done. Instead, what it looks like is happening, it's like here's my slave address again, buddy. Here's my write data, done. So I'm doing an extra thing here, or here, and it's me not. This is not like I wrote bad code. I mean, I did, but it's not like I'm misunderstanding something about how this core is working. So it's 10 o'clock. I feel like this is a decent place to stop. I have a bug to work on. I'm going to make myself a note that says what's going on. I can just rewatch this video, but have a bug. Seeing the entire transaction repeat itself. Only expect slave then data, seeing slave address data. Why the extra byte? Why? I will tackle this at a later time. Maybe it will be live stream, maybe it won't. Depends how many of you become Patreon subscribers. Just kidding. I don't know if it's going to be or not. But thanks very much for kind of watching here, hanging out with me tonight. Anybody else? Let's see what's going on here. Writing the slave address again? I think he is. Hi all. It's not a feature, it's a bug. What's up? Paul Susi, thanks for the... I missed some things here. Okay, hang on. Catching up. Labels are displayed for system Verilog. Oh, that's nice. That's good to know. I am writing the slave address again. Yeah, I think I agree with you guys. But why? I feel like I should only be doing it once. This is going to bother me. This is going to bother me. But I need to call it. So yeah, I do hope that was enjoyable for you guys. Maybe you learned some cool stuff. Maybe it was just fun to like hang out and listen to me chat while I work through some stuff. I'm not sure, but I appreciate everybody kind of hanging out. It's motivating for me to know that there's right now 35 people watching, listening, hanging out, and keep me motivated to crank out some good VHDL and Verilog tutorials. So thanks again for watching with me tonight. Take care, y'all.